Hello guys, welcome to this video on balanced three-phase circuits. Um, so in this video, we're going to look at the three-phase systems. We're going to look at analysis of the YY circuit, analysis of Y delta circuit, and the power calculations in the balanced three-phase circuits. We are going to see actually look at the power in the three-phase circuits. So in general, the reason why three-phase circuits are used is they they are used generally in power generation, in transmission, distribution, that is exploring large block of power. And so here is the you see power, you see the lines. These are these three cables corresponds to the three different phases, and we're going to look at them. So this is where the three phases mostly used. So the question is, why are three-phase systems used? Here the thing is, they generate a constant torque, there is a constant power. We're going to see this. And also because of we're going to see that in the heavy applications, like industrial applications, such as high power motors, need huge power, and so they cannot be powered using a single phase. So they need a three-phase system in order to power these devices. So the key points to note are: number one, we're going to look at the three-phase circuits, what three-phase circuits are, why a balanced three-phase circuits can be analyzed by an equivalent one-phase circuit, and how to calculate the unknowns. That is, we're going to look at what line voltages are, phase voltage, phase current, and all of that. Also, we are going to look at why the total instantaneous power of a balanced three-phase circuit is a constant. So let us look at three-phase, the sources, and in general the systems. So indeed, this diagram shows a single-phase AC generator. So it actually has a magnet and a single coil. So the single coil, we know that if this coil is rotated, it produces a current that can be dictated by this galvanometer, and the voltage can be given as such. So indeed, a single phase, let me show this diagram. A single phase or a balanced three-phase circuit would involve three of those coils. So we get a stator, which is this, in a generator, we have the stator, which is the immovable part, and the rotor. So the stator has 6 knobs, 1, 2, 3, 4, 5, 6. And so the three different wires are wound around the knobs. So you see that they are wound they face each other like this and like this. And so the angle, in order to obtain a balanced three phase, the angle between uh, consecutive knobs must be 160. So this angle is 160. And three phase, by the way, three phase balance system means that the the voltages the voltages have a phase difference of 120. So VB has a phase difference of 120 with respect to VA, and VC has a phase difference of 120 with respect to VB and VA. So that is just what it means to be balanced. So after having this, and this is a magnet. So after putting up the system, it forms the balanced three-phase system. So let's go back. And so once we mount such a system, we can have, here is this again, here is it again, here is the rotor, here is the stator. You see that this C phase right here is opposite this other C phase, and this is the axis of winding. So we have this, and we can also have this in two configurations: the source, the system, or the balanced three-phase system. We can have it as a Y configuration. This is the Y. Or we can have it as a delta configuration. You look at the shapes. Now, in general, in effect, the internal impedance of the generator is usually inductive because we have just coils, we don't have capacitance. So it's mostly inductive. And now there are the three sinusoidal voltages have the same, since we're using the phasor approach, they have the same amplitude, they have the same frequency because of the phasor approach, and we're using the phasor approach. But they also have the same amplitude because they should have the same amplitude. But what they differ in the phase, there is a phase difference of 120, as I earlier mentioned, and it's a consecutive phase. It's a consecutive difference. That is from VA, VB, VC. They're all separated by 120 degrees. So, in effect, a single configuration, be it Y, or let's say in particular, the Y configuration can have two sequences or sort of sense. So there is the positive sequence, which is the A, B, C, and there is the negative sequence. I think I should have a pencil. So the positive sequence, let me increase the size of the pencil. How can I do that? Let me just use this. So the positive sequence A, let's say it starts. So it starts, for instance, we have A, we have B, and we have C. So A, B, C, and there is a 120 degrees of them. So the positive sequence VB lags VA, and the negative sequence VA lags VB. We're going to see this. Here is it. So this is A, B, C. You label it A, B, C, and you go counterclockwise. So in this case, VB lags VA, and this is called the ABC sequence or the positive sequence. And they have a difference, a phase difference of 120. So again, if we have to look at the three-phase system in general, because the previous ones we were looking at just the source, the configuration of the source. Now, in general, to look at the three-phase system, it could be, we could have a Y configuration, Y delta, delta Y, and delta delta. So 4 different configurations. But it's sufficient enough to analyze just the Y configuration, and we can use the delta Y and Y delta transformations to get YY configuration, which is easier to analyze. So let us analyze it. So here is a general YY circuit model or configuration. So these have their names, and this right here, this is the source. You see, it has a different color. This is the source. This right here is the load. We're trying to deliver power to this. And this is the transmission line, this in the middle. So here is the source. We have the source with its internal resistance. Each source has each voltage source has its internal resistance, and this is the line. This is the transmission line, and this is the load. So this this right here is the impedance of the source. This is the impedance of the transmission line and the impedance of the load. This is the ground, the neutral line, and this one essential node and the reference. So we have unknowns to be solved. So in this case, the voltage between two lines is called the line voltage. The current that flows in a line is called a line current. And for a Y load, the line current is the same as the phase current because the same current flows in there. And of course, the voltage between the node, the neutral wire, and the line is called the phase voltage. So we have to solve the phase parameters and the line parameters. So here is an initial approach. This is so we can apply KCL. We can apply KCL here, and we see that applying KCL here or at this essential node, KCL says all current getting inside is the same as the current leaving. So this is equal to this, and that's what we have here. This equal to this. So we write that, and then we replace that with the voltages, and then we can calculate Vn if we know the impedance and the source voltages. So this is a case where it might be balanced or it is not balanced. We will show what happens when it is a balanced circuit. Now, when it is balanced, which implies this configuration is set up, where this must be 60, and then we would have this difference. So when it is balanced, we have the source voltages are made to have an equal magnitude, and of course the 120 relative phases. Now the voltage, the impedance of the source, because the same sources are used, they are the same, equal to one another, and the line impedance are the same as far as the load impedance. So the combination of the total line impedance is denoted as Z phi. Now equation 1 becomes, if we combine all of this, this becomes Z phi. So that is what we have right here. And so after calculating, looking at putting in this in place, we see that Vn is equal to 0. The node voltage. The node voltage is equal to the voltage across the Vn, the nodal voltage of this node is 0. It's the same node. So that means no voltage difference between N and big N. Between this and this, this is the neutral line. There is no voltage along this. So there is a short circuit, which means there's the V0 and there is no current flows through it, which means there's an open circuit. So we can represent it. So instead of solving the whole 3-phase, we can solve a single phase, and with the knowledge of the phase difference that we know, we can get the other voltages of the other phases. So we get